In this video, we're going to discuss synthetic strategies around electrophilic aromatic substitution. The first thing that you have to consider when trying to synthesize a more complex aromatic compound through various EAS reactions is the order of the reactions and how you're going to perform them. Because keep in mind that depending on what you add to the benzene ring, you may activate or deactivate or direct in the wrong direction. So the order of reactions does matter. So let's look at this first example. We have toluene and we are reacting with nitric acid and sulfuric acid. The methyl group on toluene is an ortho-para-director and it's also activating. So after step 1, our product is a mix of the ortho and para products, probably in fairly similar amounts. And then for the next step, we are reacting with potassium permanganate, hydroxide, and heat, and following it up with an aqueous acid workup. This is going to oxidize the methyl group into a carboxylic acid. This leaves us with O-nitrobenzoic acid and P-nitrobenzoic acid. But what if what we wanted to synthesize was the meta product, meta-nitrobenzoic acid? This would just take a flip-flopping of the reagents. So if we start off with the oxidation, after step 1, we'll have benzoic acid. Benzoic acid is going to be a meta-director because of the partial positive charge on the carbonyl carbon, and is also going to be slightly deactivating. However, if we were to add some heat, we could get this reaction to go, and we would end up with a single product, meta-nitrobenzoic acid. So this is a really simple example of this, but it does show you that the order of operations here matters. Another thing to consider is whether or not you need to utilize protecting or blocking groups in your reaction. In this example, we have kind of a weird one. The aniline has an amino substituent. The amino substituent is going to be ortho-para directing, which is great because our desired product is para. But the difficulty here is that the amino group is highly activating. And so in order to get the nitro group, we would have to add nitric acid and sulfuric acid to a highly activated benzene. That's probably not going to give us what we want. What we'll end up seeing instead is the oxidative destruction of benzene instead of our desired nitration. So what we could do instead would be to protect the aniline. So our solution here is to calm down the overreactive benzene by protecting the aniline. And the way that we're going to do that is by taking aniline and reacting it with acetyl chloride in the presence of triethylamine, which will create an amide out of the aniline. Now an amide is still going to be ortho-para directing because that lone pair is still there. It's still going to be activating, but it's not nearly as activated as aniline alone. So when you add in the nitric acid and sulfuric acid, you still end up with your nitro product in a 90% yield and a little bit of the ortho product, and you don't have to worry about the oxidative destruction of benzene because you've calmed down benzene. It's not as reactive. And then we can remove the amide by hydrolysis. This is chemistry that we haven't really learned yet. For now, you can just kind of keep this in your mind that you can remove the amide through hydrolysis. When we get to chapter 18, maybe, we talk about carboxylic acid derivative chemistry. And this will deprotect our aniline and give it back to us. Now, what if what we wanted to do was get only the ortho product from the previous synthetic scheme? That's not going to happen, right? Because we got 90% of the para product, and if our goal is to get the ortho product, we just did the most wasteful reaction in the whole world. So the better option here would be to design a synthetic scheme that allows you to favor the formation of your minor product. So we're going to block the major product from forming. we're going to take our slightly calmed down benzene and react it with concentrated sulfuric acid. This allows us to block the para position from being nitrated. Also, remember that the sulfonic acid group is removable using watered down sulfuric acid and heat, because sulfonation is our only reversible electrophilic aromatic substitution reaction. If we add in nitric acid to this same reaction, we'll end up with nitration in the ortho position, and again, none at the para because the para is already taken. And then if we add in aqueous sulfuric acid and heat, it's going to get rid of our sulfonic acid group, and that's also going to get rid of our acetyl group here. So we would end up with our desired product.